we all?
Yeah. We'll see. But yeah, they have it over in the SAC, but then they also have like a big event in the Red Barn. Y'all know the Red Barn?
Yeah.
First graduate fair was held there.
What week is this? Is this week 9?
I think week 11, week 10. Yeah.
Five weeks left. That makes sense. Week 10.
All right. Only 4? Okay, then we started. We still have a, thank you, lot of topics today. Majority still goes through this how to construct this symmetric, anisometric wave function for graphing system. In particular, we consider spin, and then we go to periodic table. So just briefly summarize here. Last class, we take an example, consider two non-interacting and identical particles, A, B, C, D. Distinguish two identical particles and two bosons, two fermions without spin. The number D is two fermions with a spin half. And the particle is limited in the one-dimensional infinite square wave. So we are going to find the energy first, ground state energy and first excited energy, as well as the ground states and the first excited states. So we use method 1 is that the construct, because it's fermions, right? Speed antisymmetric. For antisymmetric wave function, we can construct by 2 ways. Either the product of antisymmetric spatial wave function multiplied the symmetric spin function, or the symmetric spatial function multiplied the antisymmetric spin, right? So for each individual, we have the formula here. To construct antisymmetric spatial function, we use this little determinant. To construct symmetric, we use this formula, general formula, right? For construct symmetric spin, we use similar way. Construct antisymmetric spin, again we use this. So we discuss for ground state and excited states. First excited state we go through. Then we come to another method. This is more general. So this case, we consider to construct antisymmetric wave function. Immediately go to this antisymmetric, this later determinant. But here, each element of this term is the product of single particle wave function in speed multiplied spin. So that is first particle, position x1 and spin s1. Index is index of the states. So which states? ms1, just maybe plus minus, right? So that if take a half is up, we call plus, down we call minus. And the second one, second states with particle 1, particle 2. So we are going to study how to apply this one. Okay. let's first the details. I think we already know the one dimension. So each individual in the spatial, that each individual function is a particle in one-dimensional infinite square wheel. We already know this one, right? 2 over A sine n I pi x I over A, right? And for spin, any spin is here is okay. I want to make this. Let me write that. So here, because this has a 2 values, right? Because we're given s equal to half, then MSI either plus half. So we have 2 states. I have just 2 index here for this one as I, right? And this one sometimes also plus minus. So here is plus minus half over plus minus because it's just been up and down. So that if the textbook use this one, I just want to, I use different notation here because this is for spin half. You spin like 1 or more, then you have more values, so plus minus is not enough. So I usually use this index here, depend on SI, how much how much the value SI and how many MSI value. Okay. So now that is general. Now let's discuss first ground state. How to determine the ground state? The ground state's energy is lowest, right? So we first look at the energy. Energy here, okay. I think I also have the energy EI is pi square h bar square n square over 2 m3 square, right? So from here we know when the Ni is lowest number is from 1, right? Go to all the integer number. So the ground state is lowest energy. That's B. Take the lowest Ni equal to 1. So N1, 1, N2 is 1. Now, I also want to use this not as a ground since later we are going to tackle many states, so I want to just make simple as instead of say ground, I just say E naught is E1 when N1 equal to 1, N2 equal to 1, so that is sum all together. That is just pi square h bar square over m a square. Right? Okay, that's ground state energy. So that is for N1 equal to 1 equal to N2. Now we are going to construct. So here, what is N1, N2 here is equal to 1. Okay, so now let's construct this one to see how we can obtain, right? So now the ground state, there is 2 particles. That's the anti-symmetric, right? I'm going to use anti-symmetric, and again, I use not as a notation to say that is ground state. Let's follow this, right? Because we have 2 particles, 1 over square root 2 factorial, and inside here is later. So now this one, spatial is sine 1 because N1 equal to 1, right? So that is 1, x1, and here there's a plus minus, so I'm going to do here plus minus s1. There's also another 2 terms, right? So later we are going to discuss. So and say 1 second particle. This is state, right? 1, x2, and kappa plus minus s2. And second row, n2 is also 1, so here is 1. 1 plus minus s1, and 1, x2, and plus minus s2. Okay. So now we are going to construct such that the states be anti-symmetric and also non-zero, right? So here, let me okay. The possible. So that is the general, right? So okay, let me do this way. Here, we need to analyze because here, psi 1, that's the same, right? 2 row thing. Only difference come from here. So if this is plus, this is also plus, they are same, so determinant is 0, right? So here, if I take plus first, then the minus be second. So that is how to construct, because here, this one all the same. So as I said, the rows be different states, right? So this is the different state is 1, n equal to 1, but the spin is plus. Second one, n still equal to 1, but spin was minus. So that 2 states, right? So that is how to construct. Then I just, because in general I don't here, but now by analyze, we know that other follow the Pauli exclusion principle that automatically equal to 0. Now it is, so we have 2 terms, right? 2 terms is the 1, x1, and here 1, x2, and then have a plus s1, have a minus s2. Minus here, right? Minus sine 1, x1, x2, sorry, 1, x2, and kappa here, right? You can even use this kappa minus s1, kappa plus s2. And then you can see here, this thing, right? For the spatial function, the same, so I can take outside. So that is 1, x1, x2, x1, x2, sorry, 2, x1. And then the remaining part is 1 over square root 2. Now it's only spin. And you can see this is nothing but antisymmetric, the singlet states, right? So here, this one, you look here, that is for case when n1 equal to 2, n2 equal to 0, because 2 are in the same states, right? So 2 factor is 1. And here, this is 1, this is also 1, so there's no permutation. So that is one of the symmetric. Is this one, and this one is nothing but the antisymmetric here. If we take this plus, minus, add this term. So you see, even though I use the second method, but they are equivalent to the first one. So if you remember last time we discussed use this method, we discussed or try to find the ground states, and that is nothing but the symmetric in the space and multiplied antisymmetric in the spin. And that is calculation very clear. This one. Since we know the Pauli exclusion principle, we cannot add 2 atoms in the same energy, but here 2 different spin, that different, sorry, same states, different states, right? So that is the ground state. And you see the equivalent. Okay, the ground state is simple. Now let's go to the first successive state. First, how to determine first successive state? We are going to see the energy level from first ground state level, go to next one. So next one is either one of them take 1, right? Another take 1, another take 2, right? So now I also use 1 to distinguish, to replace this first, right? So that is 1 of E1 plus E2, or E2 plus E1, right? So that is, we already have this. Okay, now here that means n1 equal to 1 and n2 equal to 2, or n1 equal to 2, n2 equal to 1, right? So that is 2 cases, because they are indistinguishable, so both are give the same energy. Okay, now we are going to construct the antisymmetric function here. Okay, so psi, that is the ground states, right? So now I'm going to use first successive states, psi 1, psi 2. I'm going to the index here to be antisymmetric, but I use 1. Okay, since the symmetric, if I use the superscript, use 0 means the ground state, 1 means the first excited states. So by formula, and we are going to discuss all the possible states. So that means ny is 1, right? x1, and spin here, I'm going to say msi, there's a possible, right, as of 1. And this one, again, n equal to 1, n minus 1, so that's x2, then ms1, oh, this is not that 1, s2. And n2 is 2, the second row. Another states. So here the notation is slightly different from the textbook, but I just want to use this more general. So now you can see here, depending on how to select the MS. MS1, MS2 is a plus, all the same plus, or same minus, or one is plus, one is minus. Right? So now let's discuss. It's a possible, several possible. Now we consider case 1. Case 1 is, okay, case 1, since this will not change, right? N1, N2 will not change, only change this one. So case 1, we are going to, I'm going to use the first exact but A1, since there's another one, the generic, so we are going to give an index here. The first one is here, inside. The state, the spatial is the same, but here if I use plus, all plus is fine, right? Because they are different, so the state is still different, so I use plus. I think I use plus here. Yeah, I use plus, right? So now plus S1 and 1 x2 plus S2. Here plus S1 plus S2. That is okay because these two are not same states. So you can have, now let's just do that. So you will see I have a plus, so that you see the plus S1 plus S2, the same thing. Only difference is this, so I'm going to write down here. Two terms, x2 minus this one, right? Minus 1 x2, then 2 x1, and outside is plus S1, chi plus S2. And now you can see the first one for the spatial is this one. It's antisymmetry, equivalent, right? So that is antisymmetric. But now since this antisymmetric is different, so I'm going to use index here. Maybe here I use this 0. This for the symmetric for n here. Speak n1. So when n1 and n2 equal to 1, that is a grant. That is one, but now this one. Then the remaining part here, this one is symmetrical and antisymmetrical. If we interchange two, they are same, right? Because it stays all up. So that is symmetric. Is one of these states. And that is 2 spin up. Okay, and case 2. Second case is they are chain, right? And this chain, one is this plus this minus, another this minus this plus, they are not same. Right, so we have that's a case 2, case 3, right? So case 2. Now I'm going to create this A2. I use index different, another, and this symmetric first set states. So that by definition is phi1 x1 kappa plus s1 and phi1 x2 kappa plus s2. Then the next one is f2 x1 kappa minus s1 Because here they are not the same, since this 1 multiplied plus 2 multiplied minus, so there's 2 different states, and this is possible. Now let's do that. Okay. Here we have this multiply this, right? x2 and kappa plus s1 kappa minus s2 minus this one, right? So sin 1 x2 then 2 x1 kappa plus s2 kappa minus s1. And this one we cannot replace or equivalent to a product of special function symmetry with antisymmetry. So we keep here. And later you will see we can combine with others and get the same thing. So that is case 2. Now case 3 is opposite. Now I'm going to take the minus up plus down, right? So another state. So case 3. I1 x1 kappa minus s1 and I1 x2 kappa minus s2 is psi 2 x1 kappa plus s1 x2 x2 kappa plus s2. Just stop me when you have any question. I go maybe quickly, I show you that you can follow me. So if not, just stop and say why you write on this, and I'm going to explain. Okay, and this one we extended. So we have also 2 terms, the product, special function, and the spin is minus s1 plus s2 minus s1 x2 s2 x1 and minus s2 plus s1. Again, here they are not same, so we cannot take outside, right? So this is a minus s1, this is minus s2, right? So keep it. Now, case. Do we have one more case? Here, this is O plus. We have O minus, right? Okay. First set is number 4. So you will see we have a 4 degenerate, since we have 4 states correspond to same energy. So this one is something like case 1, since all our products is kappa minus s1, kappa minus s2, like I take outside. So inside is the only special function, the product. Minus 1, x2, x2, x1. And kappa minus s1, kappa minus s2. Here, this is antisymmetric in a special function, right? So that is psi antisymmetric, which is also first accept same thing like this, same thing like this, right? So that is, and then the remaining part is this again is a symmetric, right? But I think I need to use also index here. This symmetric is spin up. This symmetric spin down, so I'm going to use 2 s1, s2. And this same thing as the method 1. So now the remaining is 2. Case 3 and case 4, case 3, they are not, can be not written this way, but if we make the linear combination of these 2, we can also make. So now let's do that. You will see they are equivalent. So it really depends on which one you prefer to apply. And it really depends on the our knowledge of which one for us is is easier to combine. So now let's consider case 2 and 3. So if we have the linear combination of case 2 plus case 3. If I add together, right, so these two are independent, but add together I give another one, then you will see that is 1 over square root, and inside is 1 over square root. Okay, let me write down, even though it takes time. Let's write down the details. So case 2 here, right? x2 kappa plus s1 kappa minus s2. The first term, the second term minus phi 1 x2 z2 x1 kappa plus s2 kappa minus s1. That is first the case 2 and case 3 here, right? Case 3 here. Plus this one is psi 1 x1 z2 x2 kappa minus s1 kappa plus s2 minus psi 1 x2 z2 x1 kappa minus s2 kappa plus s1. 4 terms. But these 4 terms we can combine like this. You look at the spin part. So here this is the spin plus S1 multiplied spin minus S2. We have also this one, spin plus S1, spin plus. So these two can take up, right? Pick up. Then this one inside is this term. This one minus this term, right? This plus, this minus. So I have, and remember this one, so I have a first term is 1 over square root, and inside is psi 1 x1, psi 2 x2, minus psi 1 x2, psi 2 x1. And another square root 2, I have a 1 and outside and inside, right? Is this one. Is spin plus S1, spin minus S2. Is 1 and 2. And the remaining is this one. We have a minus, we have also here, this is, let me see, yes, okay. And here this minus, this plus, and so I'm going to still use plus. Plus here, right? So this is plus psi 1, x1, psi 2, x2. And then this minus psi 1, x2, psi 2, x1. And then the outside is this one, is square root, that's 1 over square root 2. Here there's a kappa plus, a kappa minus s1, kappa plus s2. Okay, so I have 2 terms, and you can see the first one is nothing but this one, antisymmetric, right? So that is, I take this outside. So I have antisymmetric in the special and multiply here. Yes?
So wouldn't case 2 and 3 by themselves not be allowed because the spatial wave function and the spin wave function are the same? They're both anti-symmetric.
They told, no, okay. When we say anti is a 2 particle, here this product is not, this itself is not anti, not symmetric. The anti-symmetric or symmetric means that, so for example, if we interchange, here we change, right? So if you change the S1, S2, it change, it's not this state, it is the other state, but it is not negative. So this one is not anti. The anti or anti-symmetric or symmetric is like, here I have, I think I'm here, you will see, okay. But this one is simple, this is a symmetric, since they are same state, so I interchange, right? So now you can see here, I have the same, right? So I take this thing, so this is n-type, right? Because this, if I interchange, that has a negative sign. So this one, the same, I take outside and I use this one. And the remaining here, 1 over square root, here, this plus this, right? Because this is plus. So that plus is pi plus s1, pi minus s2, plus pi minus s1, plus s2. Now this is symmetric. So you see here, if I interchange, they are same. Right? So if I change this one, this change, so this one is this, and this one is this, right? So they are interchanged. This is symmetric. So here, finally, I'm going to write down, this is if I combine the case 1 and case 2, add together by this, I use this one as normalized. So that is the product of any symmetric in the spatial and the symmetric in the spin. Now I'm going to use, I use S1, S2, so this is S3. That makes sense? Then this itself is not symmetric, anything, but add together when you interchange it's symmetric, right?
Okay.
Okay. So another is because we have 4 independent different states. Now if I combine 2 and 3 add together, I get another one. But if I line together, I have another way. Subtract case 2 and case 3. Then you will have another way, which is equivalent to the method 1. Okay. Since this is a little bit complicated, I'm going to write the details, let you understand how did I do it. And then next time we will. So again, so I follow the same. Only difference here is minus sign here, right? x1, z2, x2, pi plus s1, k minus s2. And the minus z1, x1, x2, pi plus s2 and minus s1. And minus here, second one, and k3. Minus s1 plus s2 minus z1, x2, z2, x1, and minus s2 and plus s1. Now in this case, I'm going to do this way. I want to find this, so this is chi minus s1 and chi minus, so these two interchange, right? So these two, wait, no. This one. Yeah, this one, right? These two. So here, this if I interchange become plus s2 is this one and minus s1 is this one. And these two are same. If I interchange become plus s1 and minus s1. So here, this term 1 and term 3 add together. So I'm going to have a square root 2, z1, x1, z2, x2. And then here, let me see, I think. Okay, so let's see. That is symmetric. All right, so here, now I got it. This is the 2, not 3. Yeah. So this one the same, right? Phi 1, S1, phi 2, S2. So only the spin not the same. So I'm going to take outside and inside the square root is have a plus S1, have a minus S2. And then here, yes, minus, have a minus number 3, right? Minus S1, have a plus S2. Yes. That is 103 here. This one and this one. Then the next one is this one. This one will have a minus sign. This minus, this also, okay, yeah. This minus, this one is minus, but minus minus plus, so we have a plus. And here this is a psi 1, x2, psi 2, x1. Second, so yes, so this one, and then here, 1 whole square root 2. So here, this is a plus, this first positive, right? So that is minus S2 and plus S1, and then minus this one, right? Minus 1 plus S2 and minus S1. Okay, so now you can see here, this one is antisymmetric. Right? This one same thing, antisymmetric. So they are same, right? And then now I can take also, now here this antisymmetric I'm going to use and take outside. Then the inside is 2 is 1 whole square root. Inside is plus, right? Psi 1, x1, psi 2, x2, plus psi 1, x2, psi 2, x1. This one is symmetric in space. Since the plus. That makes sense? So finally, you will see this product of symmetric in the spatial function multiplied with antisymmetric in space. So these are same as method 1. We obtain 4 states for the static. One is this, another 2, right? Case 1 and case 4. But if I use the second method, I have case 1, case 2, case 3 different, but actually they are equivalent. All right, so this is example. See the 2 particle. Now let's go to 3 particle. One more example, since when we have 3 particles, you will see it's more complicated. So now let's play a little bit, give you some idea, and then we can go to the periodic table. The textbook gives some of a problem and show examples, but maybe the notation is different. So I want you to use what I give you the general case and try to distinguish what they mean. 1, 2, or plus minus, right? So let's consider 3. Okay, find the 1 and first excited states of 3 promise is spin half again in 1D infinite. This is just one simple case with infinite, right? Infinite square wave. So we are going to directly use the method 2. Since the method 2 is not familiar, we are going to play more. Okay, we use method 2. So the method 2, okay, let me method 1 and method 2. Then I'm going to say why method 1 in this case. You can apply, but a little more complicated. Method 1. Let's first first, the energy again is simple, right? 3 particles, energy is individual because we consider non-intact particles. So that is fine. And the wave function should be antisymmetric, right? So that is antisymmetric. Either ground state and excited is also be antisymmetric. And this antisymmetric, if method 1 is if the antisymmetric of spatial function x1, x2, x3 multiplied spin be symmetric, or in spatial be symmetric and multiply spin antisymmetric, right? So we are going to construct both the spatial and spin function with symmetric and antisymmetric, then we multiply together, we can get. So again here, just use general, just remind you how to construct this for the spatial antisymmetric. We're going to use general formula here, right? So n1, x1, so n1, x2, so n1, x3, and then second one n2, x1, so n2, x2, so n2, x3, so n3, x1, so n3, x2, so n3, x3. And depending on n1, n2, n3, you will make up this. Symmetric. That is follow this, right? n1 factorial, n2 factorial, n3 factorial, 3 factorial, and it's for all this permutation. Now I'm going to use ij because this may be 1, 2, 1, 3, or 2, 3, right? So now n1, x1, n2, x2, n3, x3. And you'll remember how to determine n1, n2, right? So that lower n1, n2, n3, if they are equal, then give the numbers. Okay. That is for the special spin. Symmetric is easier. We follow the same thing, but antisymmetric, you will see it's not easy. Again, n1 factorial, n2 factorial. But here, this one is not this. It's correspond how many spins say, right? Okay. So be careful. Even though I use same thing. So here, communication for spin states. Hi. Okay. M_S1, S1, M_S2, S2, and M_S2, M3. For this one, antisymmetric. Here, this one we need to be careful. As I said before, because it is later, this determinant required non-zero speed, no any equal column or row, right? So we have to be careful here. That's one. Okay. Here, because Si is half, right? So the MSI only there are 2 values. So that means here, if this is plus, this minus, then another speed either plus or minus. So they have the same, at least always has the 2 rows the same, right? Which is, so that is, that means this one, okay, so number of particle, number of column, that is a number of spin. How many number of spins is larger than the number of rows. That is the number of spin states. Right? Because this. So this one, this construction is, it does not mean it's not exist, but we cannot use this one. Can not be construct. Use this formula. That makes sense? So in this case, how to do that? That we can apply additional angular momentum in chapter 7. Right? We can apply or use the addition of angular momentum. Spin angular momentum, right? Since S1, S2, okay. That, remember we have homework and also exam, right? How to apply these three spins. So you have the CG coefficients and get the different states. And then when you construct this, you're going to see which one are symmetric, which are anti-symmetric. Then we are going to apply it here. We will use this method when we go to the periodic table. So here, that method 1, I just gave you some how to do that. Now we go to method 2 in this case. Okay. Method 2, we have construct this in general the anti-symmetric. Whatever this state is first and ground state, auxiliary state, is always this letter of 3 by 3. So that is here N1, X1, MS1, S1, outside N1, X2, MS1, S2, N1, X3, MS1, S3, N2, X1, MS2, S1, N2, X2, MS2, S2, so N2, X3, MS3, S2, S3. X3, X1, M3, S1, N3, X2, MS2, or 3, S2, and N3, X3, MS3, S3. All right. So again, we know for each one, I, X, I is a, this one, right? Psi, N, I, X, I, or A. And then the any spin states is plus minus S, I, right? Okay. So now let's do the ground states and first circuits. How to construct ground state. First, look at energy, right? Energy, which method energy will not change, right? So that is the same. Energy, ground speed, I'm going to use E naught to distinguish the ground states, and you can see here all M1 and, oh sorry, it's M2. M1, M2, M3 speed take 1, right? That is the lowest energy. Okay, that is 3 h bar squared pi squared over 2 m squared. Fine. So that means we have n1 equal to n2 equal to n3 equal to 1. Now, here, all are, the index here 1, so only difference comes from spin, right? So now let's see, is possible the spin arrangements to get this ground states. Okay, side ground. HB anti-symmetric. Okay, I'm going to say to give a notation superscript 0, not a ground state. Okay, 1 over square root of 3 factorial. Now here. Do you think this is possible? I think you almost say this plus. If they take this minus, because N2 also 1, right? So here, minus, okay. The question is this one, plus minus. Whatever plus, only 2 choice, right? So that's be 0, right? Whatever you select here, say I select the plus. I have no choice for spin, right? Also, then you will see this one is 0. So what does it mean? 3 particles cannot stay at the same energy level. That is called exclusion principle. So this one is not, right? So then the ground state is not, this is not. Then they will have go to the ground state. Should be one of them go to up, right? B0, B2 at the ground. Another one should be go to 2. So that means N, okay, the numbers. I think I take yeah, that is 3. So now this, here this 1 plus 2 is 4, right? 6. 6 and over, so this factor 2 disappear, right? Okay, so N1 equal to N2, or and N3 equal to 2, or you just to dispute. So now we are going to construct the states here. Let me use the states here. So now construct ground state. So here, if I take the first 2 is N1 equal to 1, and second one equal to 2. And here, I can have plus. I take plus. Okay. Now here I have to take minus, right? Because it's 1, right? This one, they are same. So the next spin state will be different. Otherwise, it will go to 0, right? So here, I have to go to minus. Okay. S1, S1, S2, minus S2, X3, minus S3. Then here, either plus minus, right? So now I'm going to give a plus minus. So you have 2 states. Okay, yeah, I didn't. Before here, I gave the index A1. first one. So here I take, for example, I took a class. Then I have another one is take minus. So you will see the ground state actually 2 degenerate, right? 2-fold degenerate. Same thing here. The spatial function is the same, but the spin is different. Now here I give this second level is a spin down. And this one is like here. If you look at the occupation very easily. The first one, if I use this state, A1 is 2, right? These two, spin, one is spin up, one is spin down. Another one is spin up, right? And the second one is another ground state because they are degenerate. Same thing here, but here this is down. So if you use this occupation very easily to get it. All right, this ground state. Let's go to the first excited states. Here, energy. Energy is be higher than this one. So, since here I already consider the 3 particle, either this one, another up to here, right, and all possible. Then you have another is come to here, right, and this one is 1. So that is N1 equal to 1, and N2 and N3 equal to 2. There are 2. 2 particles go to 2, and 1 particle go to 1. Right, this is only one possible choice. That energy is higher than this one, right? Okay, so E, I use this, that is E1 plus E2 plus E2. That is 9 pi squared plus 4, 2, and 4 plus 1, right? 9. Okay, states. So states here. Again, we are going to use this anti-symmetric now and use 1 since it's excited states. So in general here, did I immediately separate? Okay, I need also separate. So 1 is, you will see since similar, here these 2 are in the first one, and that one, 2 are in the second one. So again, you have only the spin disputed. In second one, spin 1 plus 1, 9 minus. Another one either plus minus. So there, again, we have a 2 degenerate, right? So the first one, 1, x1, either plus, let's use plus, x1. To save time, I will not write others, right? Second one, 2, x1. Now you can use plus, s1. And then the third one is again, N2, N3 equal to 2. This be minus, right? That is one. And another one is A2 here. The first one again that is, now I cannot change these two, right? Only the first one. So now change is minus. And the second and third row the same, since they are in the same level, either plus or minus. And picture is like this. So A1, excited states, first is spin up, but the second level, 2, 1 spin down, spin up. This one spin down, spin up. The second first excited group is this one. Okay, this is also 2 degenerate, right? Any question? If not, we can go to more practical application is periodic table. So in this case, actually, you plot this one better first. You see, we have energy level, and you figure out, according to the Pauli exclusion principle, what kind of configuration they can occupy. Then with this figure, you can write down very easily, right? This is n equal to 2, this is n equal to 1. Of course, this is either n1, n2, n3, it depends, right? These 3, how to dispute it? Either n1, n2, 3 is 1, but you can only one of them is 1, the others we say, only 2 of them is here, or 2 of them here, according to Pauli principle. Okay, last topic, we have application periodic table. Why the periodic table can form all the elements in this, in the way on the table there, each element has its own position, right? Row and column. So periodic table we have is first each element has this atomic number Z. What that means? Z number of electron, right? Okay. So and then they occupy the because this electron is Fermi, right? So that's we follow the Pauli exclusion principle. Because this, so then we know we have Z electron, we cannot only all are down to the first energy level. This has to be when the first energy level failed and to go up, go up, go up. So that's why the orbital occupied for each one, each element is different since the Z is different, right? And then give a different chemical properties, physical properties, mechanical properties. That is give a diversity of the property of this element over variety. So now what we in this case, since in chapter 8 we are going to the major is how to construct the wave function for the many identical indistinguishable particles. So here they are identical, indistinguishable. Right? So how to construct the ground state wave function of the element for each element in the periodic table. So now our goal how to do this. Okay, how to do this? Now I think you're familiar with the periodic table. I don't need to print out this one for you. Now let's first consider the Hamiltonian. And then we are going to consider how to construct by consider several information, right? So first, Hamiltonian. Because so far here we always say non-interaction particles, right? But in principle it's interactive. So we are going to consider, when we construct this, we also consider several information. One is interactive between the electron and also the spin orbital coupling. Since we already learned, so right? So now let's first look at the Hamiltonian. Hamiltonian, we have the kinetic energy for each electron, Z electron, right? So I from 1 to Z. And the kinetic energy operator. I think I'm going to, since this is identical, so I don't need the index for mass, right? and the minus attractive between, this is a gas, is proton, and we have electron in different orbit here, minus E here, minus E here, and maybe minus E here. So we have attractive Coulomb potential between positive charge and negative charge, right? So how many? We have Z electron, and those are I from 1 to Z. Electron with the nucleus, right? So that is E square Z, right? And Ri minus capital R. So here is position of nucleus. This is a position of electron. And depend on here, right? So if this is R, and this is Ri as electron, if this is a coordinate here. But in general, we just select the center of this nucleus here, then the capital R disappear, right? So that is the interaction between the positive charge or electron with the proton. And we have also electron-electron interaction, that is repulsive in the same charge, right? So plus. Plus for each I electron, we have a J larger than I, since it's a pair, right? So then this is a Coulomb repulsive, Ri minus Rj. Okay, so here, this term, this one is kinetic. Kinetic energy. Okay. This one is interaction between electron and nucleus. And this one is interaction between electrons. So actually we have three terms. Oh, sorry, this one is not. This one is here. Interaction between electrons. Okay, so then the troublemaker, so far we haven't dealt with how to this one. This is a difficult part. In particular, for the many particle system, since this is a many center, right? And I, the relation between is like here, this is Ij, and then I to K, the others, right? And for each one, for this one, and this one. So very difficult is that term. Now let's make this first approximation. Ignore the electron-electron interaction. Then we are going to add that one later. First, so in that case, the Hamiltonian can be written as the summation of each individual Hamiltonian. Here, individual Hamiltonian is the kinetic energy operator plus this electron and nuclear interaction, right? Since now this summation is individual term, this summation also individual, only the sum of OI. So that can be separate. Then each one we can solve, right? So for each one is this one hydrogen lac. Item. Right? Since we have only one electron, but the nucleus is Ze, not Z. So everything the same, the result as a hydrogen atom. So now let's give it a result. This result gives us energy E index Ni, okay, that is minus E naught, which is minus 13.6 electron volt, and I square Z square. Just to remind you, chapter 6, you know, this class, right? So here E naught is constant. And Ni from 1 to integer. States. For each single electron states, if we consider spin, let's be the special function. Okay, here since let's use states Ni, Msi, psi I. Yes. Okay. Okay. And here we know this one. We can write in detail this one. We use a spherical coordinates, radial part and angular part, right? So I'm going to write this in details. R, N, L. Okay. This N, L. This together is Ni. Okay. So this Ni. Let me remove this one. Otherwise, it will be this. So. This is, I remove this one. You know the index because we have too many n, so here, but this is a radial part, only depend on the principal quantum number n and the angular momentum quantum number L, right? Just a chapter. So that is only radial part, and the angular part is a spherical harmonic, so giving L and ML, right? And then here there's a theta I, and then the spin. Spin here, I still use M as I. Now we have several quantum number. Just remember, so Ni is combination of those. So here, let me remove this one. Otherwise, this n is this n here, right? N from 1, 2, 3, all integer number. And L from 0, 1, 2, all n minus L. Then the ML is minus L plus 1 until L minus 1 is, right? And MS is, MS is plus minus half. Since we know the S is half, right? This is spin electrons half. Okay, so that means when I use index Ni for the wave function, that means include all sides of this. And the energy for n is only dependent on the principal number. But later when we consider the interaction and spin orbital spin coupling, we will discuss. So the total energy here, this for each, right? And total energy is simply E N1, N2, if we have a Z, right? And Z, we have Z electrons, with sum of O, I from 1 to Z, E N. Okay, here we use I because these single particles. And the wave function here. Wave function is antisymmetric. For the antisymmetric, then how to construct this one, we need discuss in details here. 1 over square root n factorial, and here n by n, right? So that is n1 r1 n plus S1, S1. And then this go to the end is same states, but sorry, but position is the nth particle. I see, not N. Since we have Z electrons. N S Z S1 N Z R Z M S Z S Z. Like this. Okay, let me stop here, and next Monday we are going to discuss how to do this, how to construct, find the ground states of this, each element in the periodic table. Okay. Yes, yes. Your homework I put into your box. You can pick up the uniform. Okay. Yes. And how are you? Thank you. And yes, okay, thank you. Good, good. Yes.
Could I send a PDF of my number one? Because I felt really good about getting early, so.
Uh-huh.
Use the recording from there, so
Yes,
rewrite.
yeah. Yes, sleep, okay, so sleep, will come
Yeah.
Yes, yes.
Okay.
So, let me
Yeah,
show you.
I wrote that
yes,
for the total for each UI function, so I done it for the
96.
Mhm,
Because
mhm,
you
mhm.
Okay, okay.
Yeah.
which card you
I
want.
thought-
Yeah, just use the
So you-
formula.
Okay.
Yeah.
Oh, you got. So you got blue gas, right? So you got more gas. Oh.
The problems that I felt the least confident about were
Same.
questions 2 and questions 3.
That's comfortable.
I had
I saw the challenge is question 2, but the question 2, yeah, if you follow what I did on the class for the hydrogen item, then everything is the same. The
But
only the
the
2 dimension,
difference-
3 dimension.
the difference is that in the 2 dimensions, instead of having the L squared operator gives you L times L plus 1, you have the LZ operator, which would give you M.
Mm-hmm,
H bar.
mm-hmm.
So instead of having in the like
Yeah.
radial
yeah,
function
mhm.
L plus 1, I did something like to the M.
Something like that.
So I'm not sure if that's right, but that's what I was
Something
thinking
like that,
about.
yeah, you just go to this 2 limit, right, as in topic behavior when local to 0 and local to infinite, so you can find this the envelope, and then the intermediate part is this the
Where I
topic
had
behavior.
Where I had a question though was like in my equation where I solved for the energy,
Mhm.
I had these terms for the rho and like plus 1 over rho, like equals E. So I'll be interested to see what you
You have energy as a function, as
Of
the quantum
rho.
number, right?
As the, yeah. Because I solved for E max using S max.
Yeah, something like the 3D. So then you have this one, 3D is this one, right? Summation, say, so this, if they use I use K, right? So that is RK, and the K is all the even number in this case, right? And here is equal to this one. And then you truncate until this one is equal to here, this equal to 0.
Yeah.
Use that function, then you can find the energy, right? This is what you did. Use that truncation.
I used truncation, but I didn't implement
But
that one.
this one is even or odd.
Right.
I think you probably need to find.
Well, that's okay.
Yeah, I'm going to see.
I'm sure we'll talk about it in class.
Oh, no, I made a mistake. This is for this.
For a different part.
Yeah, for this harmonic. For the
For question 1, that's what I did.
Yeah, sure. For this one, yes, you are right. There's to this thing to find this coefficient. I think we have a conflict geometry function. Sorry, here didn't discuss. But for that one, we have the A. Yeah, now I remember. Something like here, we have summation. There's A as factorial. What is
That would be
Yes.
rho z to the power of s.
Yeah, something, but anyway, this, z power to s. And if this a, s, and s go to s plus 1 is 0, then you have,
Right.
yes, you're right. Yes,
And so what
he
I'm
asked me
saying-
a question, no, I can't go to
Yeah,
that,
sorry.
yes.
I'm sorry.
Sorry, okay,
No, it's okay.
it's fine?
Yeah, it's
Okay.
fine. That's what I was trying to explain, that in that part, whenever I solved for S max to find the maximum S
Right,
value,
yes.
I found that like rho
Uh-huh.
was still in the equation for E. It didn't disappear.
Yeah.
So that's where I think I made a mistake.
Yeah, I made an arithmetic mistake and I had to rewrite everything.
Okay, I'm going to check.
Yeah.
Thanks, Dr. Yu.